Look up at the night sky, what do you see? A scattering of stars, a few planets, maybe the Milky Way stretching across the darkness. But here's the truth. What's visible to our eyes is just a whisper of the universe's full story. For every star we can spot, there are countless others hiding in the shadows, invisible to even the most powerful telescopes. Some are cloaked by cosmic dust, others lost in the glare of brighter neighbors, and a few are so bizarre, so unlike anything we've ever imagined, that they defy detection entirely. Today, we're diving into the secrets of 30 of these hidden stars, ghosts of the cosmos that exist just beyond our reach, each with a story that will reshape how you think about the universe. Picture the universe as an endless haystack, and these stars as the tiniest, most elusive needles. They're out there, warping space, bending light, or lurking in the voids between galaxies, yet we'll never lay eyes on them directly. Some are remnants of ancient supernova, their light snuffed out long before humanity existed. Others are so dense, so unimaginably heavy, that they trap even light itself in their grasp, vanishing from sight. And then there are the ones that simply don't play by the rules, stars that shouldn't exist, yet somehow do, hiding in plain sight while defying everything we thought we knew about how stars live and die. This is a journey into the unseen, where science and mystery collide. We'll explore how astronomers know these stars are there, even when they can't be seen, and what their hidden lives tell us about the universe's greatest puzzles. From black holes masquerading as stars to rogue worlds drifting alone in the dark, each of these 30 hidden wonders holds a clue to the cosmos's grandest secrets. So settle in, because by the end of this, the night sky will never look the same to you again. Deep in the frozen outskirts of our solar system, beyond the orbits of planets and even distant Pluto, lies a realm of icy mystery, the Oort Cloud. This vast shell of frozen debris stretches nearly a light year from the Sun, a graveyard of ancient comets and leftover material from the birth of our solar system. But some astronomers suspect there's more hiding in this darkness, a phantom star, drifting silently among the ice. Imagine a dim, failed sun, too small to ignite properly, yet massive enough to tug at the frozen bodies around it. This hypothetical rogue star, sometimes called Nemesis, or the Death Star in popular theories, would be nearly invisible, shrouded by the very debris that makes the Oort Cloud so difficult to study. Unlike the bright points of light we see in the night sky, this one would emit almost no warmth or visible glow, a cold ember lost in the cosmic freezer. The clues to its existence, strange patterns in comet paths. Scientists have long noticed that some comets seem to arrive in clusters, as if something nudged them inward at the same time. A hidden star, even a small one, could explain these anomalies. Its gravity would act like an unseen hand, stirring the Oort Cloud's icy inhabitants and sending them spiraling toward the Sun in eerie synchronization. Then there's the question of how such a star got there. One theory suggests it was born alongside our Sun, a twin that never matured, ejected into the darkness during the solar system's chaotic early days. Another proposes it's a wandering rogue, captured by the Sun's gravity after drifting between stars for billions of years. Whatever its origin, its presence would rewrite our understanding of the solar system's boundaries, proof that even in our own cosmic backyard, the universe still keeps its most elusive secrets just out of sight. For now, the phantom of the Oort Cloud remains just a shadow in the data, a tantalizing what-if that keeps astronomers searching. But if it's real, it's a reminder that sometimes the most fascinating discoveries aren't the ones we can see, but the ones we can only sense by the ripples they leave behind. Among the most haunting cosmic phantoms are black dwarf stars that shouldn't exist yet, but might just be lurking in the darkness anyway. These are the ultimate endgame of stars like our Sun, the cold, lifeless husks left behind after a star burns through its fuel and fades into oblivion. But here's the twist: according to our best calculations, the universe hasn't been around long enough for a single black dwarf to form naturally. The process takes trillions of years, far longer than the 14 billion years our cosmos has existed. And yet, what if one slipped through the cracks, defying time itself? Picture a black dwarf as a cosmic tombstone, a sphere of crystallized carbon and oxygen floating in the void, colder than the deepest reaches of space. Unlike white dwarfs which glow faintly with leftover heat, a true black dwarf has radiated away every last whisper of energy. It's invisible in every sense, no light, no heat, no detectable signal. But its gravity remains, warping the fabric of space-time around it like a hidden fingerprint. If one drifted near us, we wouldn't see it. We might not even feel it until it began tugging on other objects, bending starlight around its mass like an unseen lens. So how could one exist prematurely? Imagine a star born in an unusually cold, sparse region of space, where it burned its fuel at a glacial pace before collapsing into a white dwarf. Over eons, this remnant could have cooled faster than expected, perhaps by interacting with dark matter, or passing through a cloud of icy particles that siphoned away its remaining warmth. Or maybe it's a relic from a previous cosmic cycle, a survivor of a universe that existed before our own, carrying secrets we can't yet comprehend. Finding one would be like searching for a shadow in a room with no light. Astronomers would have to rely on indirect clues, an unexplained wobble in a nearby star's motion, a patch of space where light bends without a visible cause, or even a sudden, inexplicable disturbance in a cloud of interstellar gas. It's the ultimate cosmic hide and seek, where the hider doesn't just blend in, it's erased itself from the game entirely. The eerie beauty of black dwarfs is that they remind us of the universe's quiet endings. Not everything goes out in a supernova blaze or a black hole's crushing grip. Some stars simply fade, their stories ending in a whisper so faint, it's as if they were never there at all. And if one of these ghosts exists ahead of schedule, it would be a chilling reminder. The universe still has mysteries that laugh at our timelines, hiding in plain sight while we scramble to catch up. Now let's turn our gaze to one of the cosmos's loneliest love stories, a pair of rogue binary twins, cast out from their home galaxy and left to wander the void between worlds. These aren't your typical stars glowing steadily in the night. They're cosmic fugitives, either neutron stars locked in a silent gravitational embrace or white dwarfs, cold and dim, their light nearly snuffed out after eons of exile. Imagine two dancers flung from a ballroom, spinning through an empty parking lot, their movements precise but unseen. That's the fate of these nomadic twins. Once part of a crowded stellar neighborhood, they were likely ejected during a violent encounter, perhaps a close brush with a supermassive black hole, or a cataclysmic collision between galaxies. Now they drift through intergalactic space, where the distances are so vast that even their gravitational whispers go unheard. What's haunting is how little we'd know about them if they passed nearby. Neutron stars, the dense corpses of exploded giants, might emit faint pulses of radiation, but their beams would have to point directly at Earth to be detected, a cosmic lottery we're almost guaranteed to lose. White dwarfs, meanwhile, fade into near invisibility as they cool, their light so feeble it's drowned out by the glow of distant galaxies. Without the backlight of a bustling galactic neighborhood, these twins become ghosts, their presence only betrayed by the subtlest warping of distant starlight. But here's the real mystery: are they still together? Some binary pairs, separated by the violence of their ejection, might now be light years apart, forever yearning for a reunion that will never come. Others, bound by gravity's unbreakable thread, could still be locked in their eternal dance, circling one another in darkness, their movements slowing over trillions of years, until even their pirouettes freeze in the cold. The tragedy or romance of these twins lies in their silence. They could be out there right now, carrying the scars of their galactic expulsion, a testament to how even the universe's most violent acts can leave behind beauty. And though we may never spot them directly, their existence reminds us, the cosmos is full of stories written in shadows, waiting for someone bold enough to read between the lines of the dark. Somewhere out there in the cosmic dark, a star could be hiding in the most unexpected way, not by dimming its light, but by never shining at all. Meet the dark matter star, a theoretical oddball that turns everything we know about stellar physics upside down. Unlike the familiar balls of plasma radiating heat and light, these would be colossal structures built entirely from the universe's most enigmatic substance, dark matter. Picture a star that doesn't burn, no nuclear fusion, no searing surface temperatures, not even a flicker of visible radiation. Instead, it's a gravitational titan, its immense mass sculpted from particles that barely interact with ordinary matter. No spark, no glow, just pure, invisible pull. These phantom stars wouldn't merely avoid detection, they'd laugh at it, slipping through every observational net we've cast. No telescope, no matter how advanced, could spot something that doesn't emit, reflect, or absorb light. So why believe in something so elusive? The math hints at their possibility. Dark matter outnumbers regular matter 5 to 1 in the universe, clumping in halos around galaxies. Under the right conditions, and perhaps in the early universe's chaos, these particles could have collapsed into dense, star-sized knots, held together by their own gravity. Some models even suggest they'd mimic the structure of normal stars, with a core of densely packed dark matter and a diffuse outer layer, warping spacetime around them like invisible fingerprints. The hunt for these ghosts is as clever as it is frustrating. Astronomers look for anomalies, patches of space where gravity behaves oddly without a visible source. A star moving erratically, as if tugged by an unseen companion, a microlensing event where light bends without a detectable object causing it. Even the cosmic microwave background might hold clues, with subtle temperature ripples pointing to dark matter's hidden architecture. But here's the twist: if dark matter stars exist, they could solve two mysteries at once. Their gravity might explain the universe's missing mass in places where visible matter falls short. And their formation could reveal how dark matter behaves on small scales, a puzzle that's eluded physicists for decades. Of course, skeptics argue they're a fantasy, a workaround for gaps in our understanding. Yet that's the thrill of cosmology. Sometimes the wildest ideas, the ones that defy every expectation, turn out to be the keys to unlocking the cosmos' deepest secrets. Whether these shadow stars are real or not, they force us to confront the humbling truth: the universe is under no obligation to be visible to us. Some of its wonders might never glow, never blaze, never announce themselves. They simply are, cloaked in darkness, waiting for us to think outside the light. In the violent aftermath of a supernova, when a dying star collapses under its own gravity, most end up as either neutron stars or black holes. But what if some take a detour into the bizarre? Enter quark stars, hypothetical cosmic oddities so dense they make neutron stars look almost fluffy. Picture taking all the matter in Mount Everest and crushing it into a sugar cube. That's the kind of pressure we're talking about. At these extremes, even neutrons can't hold their structure. They shatter into their fundamental building blocks, quarks, the universe's tiniest Lego pieces. What makes these stars so elusive is their stealthy nature. Unlike pulsars, which scream their presence with beams of radiation, quark stars would emit almost nothing but a faint thermal whisper, a glow so dim it blends seamlessly into the cosmic microwave background, the afterglow of the Big Bang itself. Detecting one would be like trying to spot a single snowflake in a blizzard. Even their gravity wouldn't give them away easily. They'd sit right on the knife's edge between neutron stars and black holes, mimicking both just enough to keep astronomers guessing. Then there's the matter literally. Inside a quark star, protons and neutrons cease to exist. Instead, you'd find a swirling ocean of strange matter, a soupy mix of up, down, and strange quarks behaving like a single, ultra-dense fluid. Some theories suggest this matter could be indestructible, stable enough to survive outside the star, turning anything it touches into more strange matter. A single grain could, hypothetically, transform the Earth into a quark globe within hours. Thankfully, the universe seems to keep this exotic substance locked safely away in these invisible vaults. The hunt for quark stars relies on cosmic detective work. Astronomers scour data for neutron stars that seem just a bit too small or too cold, or for unexplained gaps in the mass spectrum where black holes begin. A few candidates, like a mysteriously dim object in the remnant of supernova 1987A, have raised eyebrows, but confirmation remains maddeningly out of reach. What's thrilling is the possibility that we've already spotted quark stars without realizing it. They could be hiding in plain sight, mislabeled as unremarkable neutron stars, their true nature masked by their perfect cosmic camouflage. If they exist, they'd rewrite the textbook on stellar evolution, proving the universe has one more card up its sleeve, a hidden phase of matter waiting in the dark, silent and patient, for us to finally see what's been there all along. At the heart of our galaxy, where stars crowd together like rush hour commuters, two hidden suns play an impossible game of hide and seek. They're trapped in the blinding spotlight of Sagittarius A, the Milky Way's supermassive black hole, a cosmic VIP so luminous, its glare drowns out everything nearby. Imagine trying to spot a candle flickering next to a searchlight. That's the plight of these stars, lost in the chaotic glow of the galactic core. Sagittarius isn't just bright, it's a radiation hurricane. X-rays, gamma rays, and searing ultraviolet light erupt from the material spiraling into its maw, creating a lethal fog for telescopes. Any star orbiting too close becomes a silhouette, its light smothered by this brutal brilliance. Even stars slightly farther out face distortion, their images stretched and warped by gravitational lensing, as if viewed through a funhouse mirror made of spacetime. The first of our hidden pair might be a massive, short-lived star, burning furiously but obscured by thick curtains of interstellar dust particles so fine yet so dense, they act like a cosmic smokescreen. The second could be its opposite, a cool, aging giant, its faint red glow swallowed by the black hole's blue-white fury. Both are prisoners of their environment, their stories muted by the very forces that make the galactic center such a spectacle. Detecting them demands more than just better optics. Astronomers must become cosmic detectives, parsing subtle clues, a flicker in the infrared spectrum where dust-blocked light bleeds through. A wobble in the orbits of visible stars, hinting at unseen companions tugging at them. Even the shadow of a star passing behind Sagittarius A's accretion disk, momentarily bending its light into a distorted ring, could reveal its presence. What makes these shadows special is their defiance. They endure where stars shouldn't thrive, battered by radiation, stretched by tides, yet somehow persisting. Their existence could rewrite our understanding of stellar resilience, proving that even in the universe's most hostile neighborhoods, life finds a way, or in this case, light finds a way. And so the search continues, not just for these two hidden stars, but for the countless others likely lurking in Sagittarius A's glare. They remind us that the greatest show in the galaxy isn't just the black hole's destructive spectacle, it's the quiet survivors dancing at the edge of the darkness, waiting for their moment to step into view. Some stars don't just hide in darkness, they vanish into the folds of time itself. Picture a star locked in a death spiral around a black hole, its orbit so tight that the laws of physics as we know them begin to unravel. This is the time-dilated star, a cosmic paradox where seconds stretch into eons, and light becomes a prisoner of gravity's grip. To an outside observer, this star doesn't merely dim, it appears to freeze in place, its very existence slowed to a standstill by the black hole's monstrous influence. The key lies in Einstein's theory of relativity. As the star hurtles through the black hole's crushing gravity well, time for the star ticks infinitely slower compared to the rest of the universe. Imagine watching a clock fall toward the event horizon. With each passing moment its hands would crawl, then stop entirely, never quite reaching the point of no return. The star experiences this same extreme time dilation, its light struggling to escape the black hole's pull. What little radiation does break free arrives at our telescopes stretched and weary, its wavelengths dragged into the deep red, a phenomenon called gravitational redshift. The star's once vibrant glow is smeared into near invisibility, a whisper at the edge of the electromagnetic spectrum, but the real marvel isn't just that the star fades from view. It's that from the star's own perspective, time passes normally. If you could stand on its surface, ignoring the tidal forces tearing it apart, you'd see the universe around you age in fast forward. Galaxies would spin like frantic pinwheels, stars would flare and die in moments, and cosmic history would unfold in what felt like a heartbeat. Meanwhile, to anyone watching from safety, your star would seem trapped in a single, unchanging instant, a fossilized snapshot of a moment stretched across eternity. Detecting such a star requires patience and a bit of cosmic luck. Astronomers search for strange, flickering signatures near supermassive black holes, hints of an object caught between existence and oblivion. Sometimes they spot a smear of redshifted light where nothing should be, or a subtle warp in the black hole's accretion disk, as if something unseen is skimming its edge. These clues might point to a time-dilated star, its light so distorted it blends into the background noise of the universe. The tragedy or poetry of these stars is that they're both there and not there. They exist in a limbo where physics bends to its breaking point, a reminder that the universe has stranger fates for stars than merely burning out. And while we may never see one clearly, their ghostly presence nudges us to ask, what else hides in the wrinkles of time, just beyond our ability to perceive? Long before galaxies spun into existence, before planets or even the first heavy elements were forged, the universe lit up with its very first generation of stars, the population 3 giants. These weren't just stars, they were cosmic titans, born from nothing but primordial hydrogen and helium, burning with a brilliance that outshone entire modern galaxies. Theorized to be hundreds of times more massive than our Sun, they lived fast and died violently, seeding the cosmos with the first heavy elements in colossal supernova explosions. But what if, against all odds, one of these ancient relics still lingers, untouched by time, drifting in some forgotten corner of space? Picture a lone survivor from the dawn of creation. Without metals, the elements heavier than helium that define modern stars, it would be nearly invisible to our telescopes, which rely on detecting those very materials in stellar atmospheres. Its light would be pure and unchanging, a relic spectrum untouched by the pollution of later stellar generations, and because population 3 stars were so massive, any that avoided exploding would have burned through their fuel long ago, collapsing into faint, cooling embers, ghosts of a bygone era. Finding one would be like stumbling upon a living dinosaur. Astronomers search for them in the emptiest regions of space, cosmic voids, where later star formation never took hold. These deserts, devoid of galaxies and metal-rich gas, are the perfect hiding spots for a primordial fugitive. The challenge: their light would be staggeringly faint, stretched by the expansion of the universe into the infrared, drowned out by the glow of intergalactic dust and the cosmic microwave background. Even our most advanced observatories, like the James Webb Space Telescope, would struggle to pick out such a whisper from the noise of time, yet the payoff would rewrite history. A surviving population 3 star would be a time capsule, holding clues to the universe's chemical infancy. Its composition would reveal the exact conditions of the first stellar nurseries, proving or disproving decades of theories about how the earliest structures formed. Did these stars really grow as monstrous as we think? Did they die alone or in clusters? And how quickly did they transform the pristine cosmos into the element-rich universe we know today? The haunting truth is that even if one exists, we may never find it. The universe is vast and some shadows are too faint to chase, but the search itself is a testament to our curiosity. a reach across 13 billion years to touch the dawn of light itself. And who knows, maybe, just maybe, one of those first flames still flickers in the dark, waiting to tell its story. Buried in the frozen outskirts of a distant solar system, two stars play a cosmic game of hide and seek, not behind darkness, but within shimmering cocoons of ice and dust. These aren't your typical stellar powerhouses blazing in the void. They're enshrouded twins, wrapped so tightly in debris disks that their light struggles to escape. Picture Matryoshka dolls of the cosmos, layered shells of glittering frost and rock trapping their glow like fireflies in a jar. What little radiation pierces through arrives as a distorted whisper, stretched and reddened by its arduous journey to the surface. The first of these twins might be a young, fiery star, its energy barely contained by the swirling ice that cages it. The second could be its cooler, aging counterpart, its faint blush of warmth smothered under eons of accumulated debris. Both defy easy observation, their visible light snuffed out by the very material that makes them extraordinary. Unlike protoplanetary disks, the birthplaces of planets, these structures aren't temporary nurseries. They're perpetual cloaks, relics of ancient collisions or failed planetary systems that never quite escaped their star's gravitational grip. Spotting them isn't just a challenge, it's a puzzle demanding new tools. Current telescopes see only hints, anomalous infrared glows where stars should be, or strange gaps in dust clouds suggesting an unseen gravitational anchor. But future observatories, like the next generation of space-based infrared telescopes, could peel back the icy layers. By tuning into the subtle heat signatures leaking through the cracks, astronomers might finally catch these twins in the act, their radiation warped by ice crystals into ghostly halos, like streetlights seen through a blizzard. The allure of these hidden stars isn't just their secrecy, they're time capsules preserving clues about how planetary systems form or fail. Some theories suggest they're the result of cosmic traffic jams, where wandering ice giants or rogue comets spiraled inward, shattering into vast rings. Others propose they're vampiric stars, slowly devouring their own icy moons and leaving behind glittering graves. Whatever their origin, they force us to rethink the boundaries of stellar visibility. After all, what good is a star's brilliance if the universe insists on wrapping it in frost? One day, we might not just detect them, we could eavesdrop on their frozen symphonies. The vibrations of their trapped light, the way their disks warp and ripple under stellar winds, even the chemical fingerprints of their icy shells, all hold stories waiting to be decoded. Until then, these twins remain celestial paradoxes, dazzling engines of fusion, smothered by the very cosmos they illuminate. Imagine a star that doesn't just hide in the shadows, it exists in a realm entirely beyond light. This is the neutrino star, a cosmic phantom so bizarre, it doesn't just avoid detection, it redefines what a star even is. Unlike the fiery giants we know, this one wouldn't glow, wouldn't radiate heat, and wouldn't cast a shadow. Instead, it would emit torrents of neutrinos, those ghostly, nearly massless particles that slip through planets like they're not even there. If one drifted through our solar system right now, we might never know unless we knew exactly where to look. Neutrino stars aren't just theoretical oddities, they're born from extreme physics. Picture a supernova's collapse so violent, it doesn't form a neutron star or black hole, but something stranger. Under pressures that crush atoms into a quantum soup, protons and electrons merge into neutrons, then dissolve further into a sea of quarks and neutrinos. The result, a star made almost entirely of neutrinos, bound together by forces we've barely begun to understand. It would be invisible in every conventional sense, transparent to light and radio waves, its gravity the only whisper of its presence. Detecting one would be like trying to catch smoke with your bare hands. Current neutrino observatories, like IceCube in Antarctica, are built to catch fleeting bursts from distant supernova or active galaxies, not the steady drizzle of a hidden star. Worse, neutrino stars wouldn't even emit the high-energy neutrinos our detectors are tuned for. Theirs would be low energy, slipping through Earth unnoticed, like whispers drowned out by a hurricane. To find one, we'd need an entirely new kind of telescope, one that could map the sky not by light, but by the faintest neutrino fog, yet the possibilities are electrifying. A neutrino star might not just be invisible, it could defy the very laws holding ordinary matter together. Some models suggest its core could harbor particles we've never seen, like sterile neutrinos or even dark matter precursors. Others propose it would warp spacetime differently than black holes, creating gravitational lensing effects without an event horizon. And then there's the eerie thought, could these stars be more common than we think? Floating undetected in the voids between galaxies, their collective mass might even contribute to the universe's missing matter problem. The beauty of the neutrino star is its audacity. It challenges us to rethink the boundaries of physics, to imagine a cosmos where stars don't need light to exist, and if one is ever confirmed, it'll be a humbling reminder the universe doesn't just hide its secrets in darkness. Some are written in a language we've only just begun to decipher, a lexicon of ghosts, where the very rules of visibility no longer apply. What if the star hiding in plain sight isn't just made of different material, but belongs to an entirely different universe? Meet the mirror matter star, a celestial oddity built from particles that might exist in a parallel cosmos, right alongside ours yet forever out of reach. This isn't science fiction, it's a tantalizing what-if rooted in theoretical physics, where matter could have a perfect shadowy counterpart, identical in structure but invisible because it interacts only through gravity, ignoring every other force we know. Picture a star made of mirror matter as a cosmic echo. Its protons, neutrons, and electrons would have opposite-handedness, to ours like a left-handed glove versus a right-handed one, rendering it blind to electromagnetism, the force that lets ordinary stars shine. No light, no heat, no radiation, just gravity's faint tug, the only whisper of its existence. If one drifted into our solar system, it wouldn't collide with planets or scatter sunlight. It would phase through everything, silent as a ghost, detectable only by the way its mass bends the paths of visible stars behind it. Theories suggesting such stars exist come from an audacious idea that the Big Bang didn't just create our universe, but also a mirrored twin, a separate reality where particles spin the opposite way. In that universe, mirror stars would blaze visibly, but here, they're phantoms. Some physicists argue this could solve cosmic mysteries, like why galaxies rotate faster than their visible matter suggests. These invisible anchors woven into the fabric of space might be the missing mass we've labeled dark matter. Hunting mirror stars requires rethinking how we observe the cosmos. Astronomers search for unexplained gravitational lenses, patches of space where light bends without a visible culprit. A few anomalies, like the baffling dark galaxy Dragonfly 44, which weighs as much as the Milky Way but emits 1% of the light, have sparked debate. Could these be clusters of mirror stars, their collective gravity warping spacetime while their particles refuse to announce themselves? The beauty and frustration of mirror matter is its perfect camouflage. Even if one brushed against Earth, our sensors would miss it, unless we invent ways to measure gravity's subtlest ripples with unprecedented precision. Future observatories, like space-based gravitational wave detectors, might finally lift the veil, catching the faintest tremors in spacetime caused by these invisible giants. What keeps physicists awake at night isn't just whether mirror stars exist, it's the dizzying possibility they're everywhere, woven into the cosmos like threads in a tapestry we've only seen from one side. If proven, they'd rewrite not just astronomy but our understanding of reality itself, proving the universe has always been richer, stranger, and more crowded than our eyes could ever see. Among the universe's strangest hidden stars, none bend the rules quite like the Kugelblitz fireflies, twin cosmic enigmas forged not from matter, but from pure, concentrated light. These aren't stars in any traditional sense. They're the offspring of an Einsteinian fever dream, where light itself collapses into a gravitational prison, birthing a black hole from energy alone. Picture two pinpricks of spacetime, each smaller than an atom yet heavier than a mountain, their existence so fleeting and subtle, they slip through the cracks of detection like shadows at noon. The magic or menace of these fireflies lies in how they form. In theory, if you could focus an unfathomable amount of light into a single point, its energy would warp spacetime so severely that it buckles into a black hole. No star death, no crushing matter, just raw photons squeezed until they become their own grave. The result, a Kugelblitz, German for ball lightning, a black hole born from the very thing meant to illuminate. And if two of these formed in tandem, perhaps from a cataclysmic gamma-ray burst or an alien-scale laser, they'd orbit each other in a silent, invisible dance, their presence betrayed only by the faintest tremors in the fabric of reality. What makes them truly ghostly is their defiance of time. Most black holes evaporate via Hawking radiation, leaking particles over eons until they pop out of existence. But Kugelblitz fireflies, if tiny enough, would vanish almost instantly, too quickly to emit a single detectable particle. They'd blink into being and vanish before any instrument could react, leaving behind not even a ripple of radiation. The universe's ultimate mayflies, here and gone in a cosmic heartbeat. Then there's the chilling question, could they be artificial? The energy required to create them is beyond anything nature routinely conjures, but not beyond the reach of a civilization mastering interstellar engineering. Imagine a distant culture encoding messages in the timing of their Kugelblitz births, or using them as quantum-scale supercomputers, their minute event horizons processing information at the edge of physics. Or worse, as weapons, microscopic black holes hurled through space, swallowing planets from the inside out, yet even if they're natural, their rarity would make them priceless cosmic artifacts. A single confirmed detection would prove light alone can bend the universe to its will, opening doors to technologies and truths we've barely dared to imagine. Until then, the Kugelblitz fireflies remain hypothetical marvels, a reminder that sometimes the universe's most dazzling secrets are the ones that cast no shadow at all. Far beyond the Milky Way's bustling spiral arms, where the light of billions of stars fades into the void, an ancient wanderer drifts in silent solitude. This isn't some luminous giant or explosive remnant, it's a galactic ghost, a brown dwarf so faint and cool it barely qualifies as a star at all. Born in the chaos of the early universe, this celestial relic has spent over 13 billion years cooling into near invisibility, its feeble glow drowned out by the brighter, younger stars of the galactic disk. Brown dwarfs like this one occupy a strange twilight zone too massive to be planets, yet too small to ignite sustained fusion in their cores. They're the universe's forgotten embers, simmering at temperatures colder than a campfire, their light stretched into the infrared by time and distance. This particular wanderer, adrift in the Milky Way's halo, a sparse, spherical shell of stars and dark matter surrounding the galaxy, is a master of evasion. Its dimness isn't just a quirk, it's a survival tactic. Most sky surveys are tuned to spot brighter objects, leaving these cosmic introverts to slip through the observational net. What makes it even harder to find is its loneliness. Unlike stars in crowded galactic neighborhoods, this one has no companions to give it away through gravitational tugs or transits. It moves through the halo like a shadow, its presence betrayed only by the rarest of alignments, when its gravity briefly bends the light of a background star, a phenomenon called microlensing. Even then, the signal is whisper quiet, often lost in the noise of more dramatic cosmic events, yet this wanderer's obscurity hides a fascinating story. Its composition is a time capsule from an era before heavy metals polluted the cosmos. Without elements like iron or silicon to absorb its already dim light, its spectrum is strikingly pure, a relic of the universe's chemical infancy. Some theories suggest brown dwarfs in the halo could be among the very first objects to form after the Big Bang, making them not just hidden stars, but cosmic elders carrying secrets from the dawn of time. The challenge of spotting them is also a lesson in humility. Our galaxy's halo may be teeming with these fated giants, each a silent witness to epochs long past. Future telescopes, like the Nancy Grace Roman Space Telescope, could finally bring them into focus by scanning vast swaths of sky for the subtle fingerprints of their gravity. Until then, they remain ghosts of the halo, faint, forgotten, and waiting for their stories to be told. Some stars don't just fade into the darkness, they're stretched into oblivion by the universe's own flaws. Floating between galaxies where gravity's grip is weakest, lies a cosmic needle threading through space, a defect in spacetime itself called a cosmic string. These hypothetical relics from the Big Bang are thought to be unimaginably thin yet denser than neutron stars, curling through the cosmos like invisible wires. And if one drifted between us and a distant star, it wouldn't just bend the light, it could magnify the star into nothingness. This is the cruel irony of gravitational lensing pushed to its extreme. Normally, massive objects like galaxies or black holes gently warp the light from stars behind them, creating elegant rings or arcs, Einstein's cross being the most famous example. But a cosmic string doesn't play by those rules. Its gravity is so concentrated, so razor-thin, it would slice the star's light into parallel beams, warping its image into two perfect, identical copies separated by a hair's width in the sky. At the right distance, though, something even stranger happens. The string's lensing becomes so severe that the star's light stretches into an infinite smear, its photons spread so thin across the sky that no instrument could ever piece them back together. The star wouldn't just be distorted, it would be erased by its own magnified glow. Here's where physics turns surreal. Unlike black holes which swallow light whole, cosmic strings would theoretically leave no shadow, no event horizon. They're more like cracks in reality, bending spacetime with surgical precision. If one passed through our solar system, we might not even notice, until distant stars began flickering in impossible pairs or vanishing entirely, their light stretched beyond the limits of detection. Astronomers searching for these phantom strings look for these telltale double images or sudden, unexplained disappearances in stellar catalogs. So far, no confirmed sightings exist, just tantalizing gaps in the data, places where the math suggests something invisible might be threading the cosmic tapestry. The eerie beauty of this idea is that it flips our understanding of visibility upside down. We think of darkness as the great concealer, but here, it's light itself that becomes the ultimate camouflage. A star, bright enough to blaze across galaxies, could be hiding in plain sight, smeared across the void by a defect older than time, waiting for us to learn how to see the universe's hidden stitches. Deep within the swirling heart of a turbulent galaxy, two stars wage a silent battle against invisible forces, not with gravity, but with magnetism. These are the plasma vortex twins, trapped in a labyrinth of superheated plasma currents so intense, their light is shredded into a chaotic blur. Picture a lighthouse beam swallowed by a hurricane, its guiding signal scattered into 1,000 fractured glimmers. That's the fate of these stars, their radiance twisted and smeared by the galaxy's own magnetic fury. The twins' prison isn't made of dust or gas, but of something far more elusive, colossal plasma loops, writhing like electric serpents around the galactic core. Charged particles spiral at near light speeds, weaving a web of magnetic fields so powerful, they bend not just light but the very paths of stars caught in their grasp. One twin might be a massive blue giant, its ultraviolet scream diffused into a ghostly haze. The other could be a smaller, cooler star, its reddish glow stretched into long, faint tendrils by the plasma's relentless churn. Together they orbit each other in a dance distorted by forces neither can escape, their true forms hidden behind curtains of ionized chaos. Astronomers suspect these twins exist because of telltale gaps in the data patches of space where energy signatures suggest stars should be, yet no direct light arrives. Sophisticated models trace these voids back to the galaxy's most violent regions, where magnetic fields are strongest. It's like listening for a whisper in a thunderstorm. The star's faint radio pulses, warped by plasma, sometimes leak through the noise, revealing their approximate locations. Other clues come from the plasma itself, which flickers in unnatural patterns, as if something massive is stirring it from within. The irony is that without their turbulent prison, these twins would be dazzling. The blue giant, if freed, could outshine most stars in its galaxy. Its cooler companion might host planets basking in its glow. Instead, they're cosmic prisoners, their brilliance sacrificed to the galaxy's invisible machinery. Yet their struggle holds a key to understanding how magnetic fields shape galactic evolution, and how even the brightest stars can vanish into the universe's hidden currents. Future telescopes equipped to map magnetic fields in unprecedented detail might finally tear away the plasma veil, exposing these twins to view. Until then, they remain spectral enigmas, their light scattered like shards of a broken mirror, waiting for someone to piece together the reflection. At the very edge of what physics dares to imagine, there might exist a star so deeply entangled with the fabric of reality that it defies the very concept of visibility. This is the quantum foam star, a celestial phantom woven into the chaotic froth of spacetime itself. Picture the universe at its smallest scales, where space isn't smooth and continuous, but a seething, bubbling ocean of virtual particles flickering in and out of existence. Now imagine a star caught in that storm, its presence smeared across probabilities rather than fixed points, more a ripple in the cosmic code than a tangible object. The key to its invisibility lies in Heisenberg's uncertainty principle, the rule that says we can never perfectly pin down both a particle's position and its momentum. For ordinary stars, this barely matters. Their vast scales smooth out quantum weirdness, but a quantum foam star would exist at the threshold, where uncertainty isn't a minor effect but the star's defining feature. Its mass, its light, even its location would be fundamentally blurry, like a fingerprint left on wet glass. Telescopes searching for it would find only statistical ghosts, hints of something maybe there, flickering at the edge of detection before dissolving back into the foam. What's wilder is how such a star might form. One theory suggests it's the remnant of a supernova so violent, its collapse triggered quantum gravitational effects, freezing the star mid-implosion. Instead of becoming a black hole or neutron star, it's suspended in a state of perpetual almost, neither fully collapsed nor fully stable, its matter stretched across Planck-length dimensions. Another idea posits it as a cosmic accident, born in the early universe when spacetime's foam was thicker, a stellar seed that never fully escaped quantum turbulence. Detecting it would require rethinking observation itself. Traditional astronomy relies on photons arriving predictably from fixed points, but a quantum foam star's light would arrive scrambled, its photons emerging from the foam at random angles and energies, like Morse code transmitted through a tornado. Even its gravity would be unpredictable, warping spacetime in fleeting, unpatterned ways that defy mathematical modeling. The only clues might come from anomalies, patches of space where gravity spikes erratically, or where background radiation carries inexplicable statistical noise. The implications stagger the imagination. If such stars exist, they'd prove that quantum physics doesn't just govern atoms and particles, but can scale up to celestial proportions. They'd challenge our definitions of what a star even is, blurring the line between object and phenomenon, and they'd hint at something profound, that the universe hides its most radical experiments not in distant galaxies, but in the folds of reality itself, where the rules we know dissolve into possibility. Perhaps the most haunting thought isn't whether we'll find one, but whether we already have. The cosmos is littered with gravitational anomalies and unexplained energy fluctuations, dismissed as noise or instrument error. Could some of them be quantum foam stars, whispering from the void in a language we're only beginning to decipher? Until we learn to listen differently, they'll remain the ultimate cosmic secrets, not just hidden, but woven into the very fabric of hiding. Think of the universe running on autopilot for an unimaginable stretch of time so long that even the slow decay of protons becomes inevitable. Now picture this: amidst that near-infinite silence, pure randomness conspires to assemble, against all odds, a fully formed star. Not through gravity or fusion, but by the sheer statistical whimsy of quantum fluctuations. This is the Boltzmann star, a cosmic mirage born from the same mind-bending logic that gives us the Boltzmann brain paradox, the idea that, given enough time, random particle arrangements could momentarily mimic conscious beings. Only here the universe isn't assembling a fleeting mind, it's stitching together an entire stellar furnace from chaos. The numbers involved are laughably improbable. For a Boltzmann star to blink into existence, every atom in its structure would need to randomly align in precisely the right configuration not just once, but continuously, long enough for it to briefly ignite. The odds are worse than shuffling a deck of cards into perfect order trillions of times in a row. In fact, the expected time for such an event dwarfs the current age of the universe by more zeros than most calculators can display. It's the ultimate cosmic lottery, where the prize is a star that shouldn't exist, and the jackpot is rigged to never pay out. But here's where physics gets surreal. If one did form, it wouldn't just be hard to spot, it would erase itself from reality almost instantly. Quantum fluctuations are fickle. The same randomness that birthed the star would tear it apart nanoseconds later, its atoms scattering back into the void like a sandcastle swallowed by the tide. There'd be no lingering light, no gravitational echo, just a blip of energy so brief, our instruments would dismiss it as noise. Even our most sensitive detectors, tuned to catch the shortest gamma-ray bursts or neutrino pulses, would struggle to separate its death rattle from the universe's background static. Yet the Boltzmann star isn't just a thought experiment, it's a stress test for our understanding of probability, entropy, and the arrow of time. Some cosmologists argue that if the universe truly lasts forever, these statistical ghosts must appear occasionally, if only to taunt us with their impossibility. Others counter that the math is a warning, a sign that our theories break down when stretched across eternity. Either way, the Boltzmann star serves as a humbling reminder: the universe doesn't need purpose to create. Sometimes chaos alone is enough to spark a fire in the dark, even if it's a fire that vanishes before anyone can see it. Somewhere in the vast expanse of the cosmos, two stars are performing the ultimate vanishing act, not by dimming or collapsing, but by fleeing faster than the very light they emit. These are the dark energy echoes, twin celestial bodies caught in the grip of the universe's accelerating expansion, receding from us so rapidly that their photons will never bridge the growing chasm between us. They aren't hiding behind dust clouds or cloaked in exotic physics, they're being erased by the relentless stretching of spacetime itself, their existence reduced to faint tremors in the fabric of reality. Picture a river flowing faster than a swimmer can paddle. No matter how hard the swimmer strains against the current, they'll never reach the shore. That's the fate of light from these stars. As the space between us and them expands faster than light speed, their photons, despite racing toward us at 299,192 kilometers per second, are carried backward like runners on a cosmic treadmill. The result, a paradox where the stars still exist, yet their light is eternally exiled, their images frozen at the edge of our observable universe like figures in a painting we'll never touch. But here's where it gets stranger: though their light is lost to us, their gravity isn't. Spacetime's curvature, unlike light, isn't bound by speed limits. The mass of these fleeing stars still warps the universe around them, creating subtle ripples that propagate outward like echoes in an endless hall. Future gravitational wave detectors, sensitive enough to catch the faintest whispers of colliding black holes or neutron stars, might one day pick up their murmurs, distortions in the void with no visible source, the only fingerprints of stars that have effectively left our reality. Their story begins with dark energy, the mysterious force accelerating the universe's expansion. In regions where this force dominates absolutely, galaxies, stars, and even space itself are wrenched apart. For our twin stars born in one such region, the moment their home galaxy crossed the cosmic horizon, the point where space's expansion outran light's speed, they became phantoms. To civilizations in their own galaxy, they might still shine brightly, but to us they've crossed into a shadow realm, their light stretching into longer, redder wavelengths until it dissolves into the cold background hum of the cosmos. What's tragic is how ordinary these stars likely are. They could be yellow suns like ours, orbited by planets lush with life, their skies filled with constellations we'll never map. Or they might be white dwarfs, cooling into obscurity, their final sighs of heat lost to the void. Their fate isn't dictated by rarity or oddity, but by cruel geography and accident of cosmic placement that's rendered them invisible not just to our eyes, but to any instrument reliant on light. Yet their gravitational echoes offer a haunting kind of hope. If we can learn to listen to spacetime's vibrations with enough precision, we might someday reconstruct their presence from the warps they leave behind, like dedosing a storm's passage from the wreckage it scattered. It's a reminder that even as the universe tears itself apart, it leaves traces of what's been lost, whispering secrets in a language deeper than light. The universe has a way of hiding its greatest tricks in plain sight, like a star that isn't truly there in the way we think. Imagine gazing at what appears to be a brilliant point of light, only to realize it's not a three-dimensional object at all, but a projection, a cosmic hologram etched onto the fabric of spacetime itself. This is the holographic star, a celestial illusion born from one of physics' most radical ideas, the holographic principle. At its core, the principle suggests that all the information in a given volume of space, every particle, every force, even the star we think we see, can be encoded on a two-dimensional surface at its boundary, like a DVD storing a 3D movie. In this scenario, the star isn't burning in the void, it's painted onto the cosmological horizon, its light and heat mere projections from data written on the edge of the observable universe. To us it looks and behaves like a star, emitting light, warping spacetime, even casting shadows, but in reality, it's a shadow play of a deeper, hidden reality. Why would such a star be invisible? Because the surface encoding it lies far beyond our observational reach. The holographic boundary isn't some nearby screen, it's the farthest edge of the cosmos, where the expansion of the universe carries information away faster than light can travel back to us. Any star stored there would be physically real in its effects, yet its source would forever lie outside our causal reach, like a reflection in a mirror that's been shattered and scattered across time. Detecting a holographic star would require rewriting the rules of observation. Traditional telescopes are useless here. They capture light from objects, not the quantum bits on a distant horizon. Instead, we need to look for anomalies, gravitational lensing patterns that don't match any visible mass, or stars whose properties seem mathematically too perfect, as if generated by an underlying code. Some theorists even suggest that certain ultra-precise pulsars, whose beats are unnaturally regular, might be cosmic glitches, artifacts of the universe's holographic rendering. The implications are staggering. If holographic stars exist, they'd be proof that reality is fundamentally informational, a simulation running on the universe's deepest hardware. They'd blur the line between what's real and what's projected, forcing us to question whether any star is truly independent, or if all are just pixels in a grand cosmic display. Yet the most haunting thought isn't whether we'll find one, it's that we might never know for sure. The holographic principle, while elegant, is notoriously difficult to test. A holographic star could be right in front of us, and we'd have no way to distinguish it from the real thing. It's the ultimate cosmic sleight of hand, a reminder that the universe's greatest magic tricks aren't just about hiding things, but about convincing us they were never hidden at all. In the vast catalog of cosmic oddities, few hypothetical stars defy our understanding of physics as completely as the magnetic monopole star, an object built from particles that, as far as we know, don't even exist. At least not yet. Magnetic monopoles are the unicorns of particle physics, theoretical particles that carry a single magnetic charge, either north or south, unlike the paired poles we're familiar with in everyday magnets. If nature allows such particles to form, they could clump together under gravity, creating a star unlike anything we've ever imagined. Picture a star where magnetism isn't a byproduct of swirling plasma, but the very foundation of its existence. Instead of generating magnetic fields through motion, like Earth or the Sun, this star is magnetism incarnate, a dense knot of pure north or south poles, repelling and attracting each other in a delicate dance. Its structure would be a labyrinth of force lines, twisting into impossible geometries. With no opposite poles to neutralize them, these fields could stretch across light years, weaving invisible patterns through space without the telltale glow of charged particles. Why would such a star remain hidden? Conventional astronomy relies on detecting light or gravitational influence, but a monopole star might emit neither. Its magnetic fields wouldn't accelerate electrons to produce radiation, leaving it dark across the electromagnetic spectrum. Even its gravity could be negligible if it formed from ultra-light monopoles, hypothetical particles with masses far below those of atoms. The only way to spot one would be to catch its magnetic fingerprint, warping the paths of cosmic rays, or distorting the polarization of distant starlight, subtle clues buried in oceans of interstellar noise. The hunt for monopole stars is tied to one of physics' greatest unanswered questions. Why does our universe seem to lack magnetic monopoles, despite theories predicting their existence? Some models suggest they were abundant in the searing heat of the Big Bang, but annihilated instantly, leaving behind only their influence on the universe's expansion. Others propose they're hiding in plain sight, woven into the fabric of neutron stars or lurking in the voids between galaxies. A monopole star would be the ultimate vindication of these ideas, a celestial monument to the universe's hidden symmetries. What's most tantalizing is the possibility that these stars could be cosmic powerhouses in disguise. If monopoles can catalyze proton decay, a wild but plausible idea, their stars might emit faint bursts of gamma rays as they slowly convert ordinary matter into energy. Telescopes like the Fermi Gamma Ray Space Telescope have sporadically detected unexplained flashes that fit this profile, though proof remains elusive. Whether monopole stars are real or not, they embody the audacity of theoretical physics, a field unafraid to imagine the unimaginable. They challenge us to look beyond light and gravity, to consider that the universe's grandest secrets might be written in the silent language of magnetic fields, waiting for us to learn how to read them. Among the most unsettling possibilities, the universe might harbor our stars imprisoned behind walls of pure, impenetrable physics, not cloaked in dust or distance, but banished to alternate realities by the very fabric of space itself. These are the vacuum decay bubbles, cosmic anomalies where the rules of reality shift so dramatically, entire stars could be locked away in pockets of existence with different fundamental constants. Picture two stars, identical in mass and composition to those we know, yet separated from our universe by an energy barrier so absolute, not even light could cross it. They're not just hidden, they're exiled, their fates dictated by a quirk of quantum fields most of us will never comprehend. The horror or fascination of vacuum decay lies in its origins. According to quantum field theory, the vacuum of space isn't truly empty. It's a seething, bubbling soup of potential energy, stabilized by the Higgs field that gives particles their mass. But what if that stability is an illusion? Some theories suggest our vacuum might be a false state, teetering on the edge of a more stable, lower energy configuration. If triggered by cosmic rays, particle collisions, or sheer quantum randomness, a bubble of this true vacuum could expand at light speed, rewriting physics as it goes. Inside that bubble, stars would still burn, planets might still orbit, but the fundamental forces governing them could be so altered, their light would never reach us. The energy wall at the boundary would act as a one-way mirror. We'd see nothing, while inside, an entire stellar system might carry on, oblivious to its exile. How would we even suspect such stars exist? Their presence would betray itself in the subtlest ways. One clue lies in gravity, the one force that might still leak across the barrier. Astronomers could detect unexplained gravitational lensing, where light bends around what appears to be empty space, hinting at mass trapped in an invisible pocket. Another signature might be the sudden disappearance of stars, not by dimming or explosion, but by an abrupt severing from our reality, as if snipped out of the cosmos by scissors made of pure energy. The most chilling possibility, these bubbles could be growing right now, their edges expanding undetected until they rewrite physics at our doorstep. The irony is that vacuum decay bubbles might be both profoundly rare and terrifyingly common. They could be scattered throughout the universe, remnants of early cosmic instability, each a frozen snapshot of physics operating under different rules. Some theories even suggest entire galaxies could be locked inside them, their stars shining under alien laws of electromagnetism or nuclear force, yet for all their menace, they also offer a bizarre kind of hope. If civilizations inside these bubbles survive, they've mastered physics beyond our wildest dreams, turning existential catastrophe into a new normal. For now, the search for these phantom stars remains a blend of paranoia and poetry, tiny fluctuations in cosmic microwave background data, anomalies in quantum experiments, or even inexplicable gaps in stellar distributions might one day reveal their presence. Until then, they stand as cosmic wildcards, proof that the universe's greatest secrets might not just be hidden in darkness, but sealed away in realities where the very definition of star no longer applies. Hidden among the cosmos could be a star that doesn't just ignore the rules of physics, it plays by an entirely different rulebook. This is the fifth force star, a celestial oddity that doesn't communicate through the familiar channels of gravity or electromagnetism, but through an invisible, undiscovered fundamental force. While the universe as we know it runs on four forces: gravity, electromagnetism, and the strong and weak nuclear forces, this phantom star might be tugging at the fabric of reality in ways we've yet to imagine, leaving no trace of light, heat, or even the faintest radio whisper. The key to its elusiveness lies in its refusal to engage with electromagnetism, the force that makes stars visible in the first place. Ordinary stars blaze because their superheated plasma generates photons, particles of light that travel across space to reach our eyes and telescopes. But a fifth force star wouldn't produce or interact with photons at all. It would be utterly dark, its presence betrayed only by the subtle sway it exerts on surrounding objects through this mysterious fifth interaction. Picture a puppeteer manipulating marionettes. While standing just outside the stage lights, the movements are visible, but the hand guiding them remains unseen. So what might this hidden force look like? Theoretical physicists have toyed with the idea of a dark photon, or a force that operates only in the shadows of dark matter, influencing massive objects without leaving the usual electromagnetic fingerprints. Some models suggest it could be a long-range force, weaker than gravity but far-reaching, threading through galaxies like an invisible web. Others propose it might work only at extremely short ranges, binding particles within the star so tightly that its effects vanish beyond a certain distance. Whatever its nature, its existence would rewrite our understanding of how the universe holds itself together. But if we can't see it or detect its radiation, how would we ever find such a star? The answer lies in anomalies, places where gravity alone can't explain what's happening. Astronomers might spot a cluster of visible stars orbiting nothing, their paths warped by an unseen mass. Or they could detect gravitational lensing, where light from distant objects bends around empty space, with no black hole or dark matter halo to account for the distortion. Even more intriguingly, the fifth force itself might leave subtle imprints on the cosmic microwave background, the afterglow of the Big Bang, as if the universe quietly recorded its presence billions of years ago. The implications are staggering. If a fifth force star exists, it wouldn't just be a curiosity, it would be a revolution. Proving the existence of a new fundamental force would unlock doors to technologies and energies we can barely conceive. It might explain why dark matter seems to clump in ways gravity alone can't justify, or why certain particles behave unexpectedly in high-energy experiments. And philosophically, it would remind us that for all our telescopes and equations, the universe still holds fundamental truths we haven't even begun to grasp. For now, the fifth force star remains a tantalizing what if, a ghost in the equations of physicists and a challenge to astronomers, but if one is ever confirmed, it will prove that some of the cosmos' greatest wonders aren't just hidden in darkness, they're written in a language we're only now learning to speak. At the very beginning of time, when the universe was a seething, unfathomably dense soup of energy, something extraordinary may have condensed out of the chaos, not a star, not a planet, but a black hole born from the raw pressure of creation itself. This is the primordial black hole, a relic from the Big Bang so ancient, it predates the first light of the first true stars, and if one exists today, camouflaged within a shroud of accreted matter, it could be the ultimate cosmic imposter, a black hole disguised as a star, hiding in plain sight. What makes this phantom so unsettling is how perfectly it could mimic a stellar presence. Most black holes announce themselves violently, through the X-ray screams of matter spiraling into their event horizons or the gravitational waves of collisions. But a primordial black hole, especially one with the mass of a typical star, could cloak itself in a shell of gas and dust, quietly pulling in just enough material to glow like a dim, cool star without ever revealing the abyss at its core. Picture a campfire built atop a bottomless pit. From a distance you'd see only the flickering flames, never the darkness feeding beneath them. The debate among physicists hinges on balance. Could such a black hole accrete matter at precisely the right rate to sustain a stellar illusion without betraying itself? Too much infalling gas, and the resulting radiation would reveal the telltale fingerprints of a black hole's accretion disk, jets of plasma, intense X-rays, or time dilation effects. Too little and the star would appear unnaturally cold and faint, a red flag for astronomers, but in the Goldilocks zone between these extremes, the deception could be flawless. Some models even suggest these imposters might pulse like variable stars, their brightness subtly fluctuating as the black hole's gravity tugs and compresses its gaseous cloak. The hunt for these cosmic doppelgangers focuses on the universe's quietest corners, regions where dim, cold stars seem out of place. Astronomers scrutinize anomalies, a star that's far older than the surrounding stellar population, one that moves through space with no known origin, or an object emitting just a fraction of the light expected for its mass. Even more telling would be a star lacking the chemical signatures of fusion, no hydrogen burning into helium, no heavy elements forged in its core. These ghosts wouldn't just hide their true nature, they'd lack the very processes that make stars what they are. Yet the implications stretch beyond mere cosmic hide and seek. If primordial black holes exist, they could solve mysteries plaguing modern astrophysics, like the identity of dark matter. While most theories focus on exotic particles, some suggest these ancient black holes, sprinkled throughout the universe, might account for the missing mass holding galaxies together. Others speculate they could be the seeds of supermassive black holes found at galactic centers, having grown over billions of years by devouring stars and gas. The most haunting possibility, we might have already spotted one and mistaken it for something ordinary, hidden among the countless stars in our catalogs. One of those faint, unremarkable dots could be a fossil from the dawn of time, wearing a stellar mask so convincing, even our best tools are fooled. Until we learn to see through the disguise, the universe's first black holes will keep their secrets, lurking in the light while whispering truths only gravity can tell. How do you find something designed to stay unseen? Astronomers chasing hidden stars face this paradox daily, armed with tools that push the boundaries of modern science. One of their most powerful techniques is gravitational microlensing, a cosmic trick where the gravity of an invisible object bends and amplifies the light of a background star, revealing its presence like a fingerprint on a lens. Imagine holding a magnifying glass over a distant street lamp. As you move the glass, the lamp's light flickers and brightens. In space, that magnifying glass is a hidden star's gravity, and the flicker lasts weeks or months, creating a telltale signature in telescope data. Recent projects like the optical gravitational lensing experiment have used this method to uncover free-floating planets and rogue brown dwarfs, but the real prize would be catching a primordial black hole or a neutrino star mid-lens, their mass-warping starlight without a visible trace. Yet microlensing has limits. It's a waiting game, requiring perfect alignment between observer, hidden object, and background star, a cosmic coincidence that might happen once for every million stars monitored. Worse, the signal is fleeting. By the time astronomers spot a lensing event, the invisible culprit has often drifted out of view forever. That's where neutrino detectors step in, hunting for stars that shun light but can't hide their subatomic whispers. Facilities like Super Kamiokande in Japan and IceCube in Antarctica are tuned to catch neutrinos from supernova, but they've also become traps for more exotic quarry. A neutrino star, if one exists, would emit a steady drizzle of these ghostly particles, creating a faint but recognizable pattern in the data. The challenge: distinguishing this signal from the neutrino noise of the sun, cosmic rays, and distant black holes, a task akin to picking out a single violin in a symphony played at the edge of the universe. Enter artificial intelligence, the game-changer in this cosmic hide-and-seek. Modern sky surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will generate petabytes of data, far more than human eyes can process. Machine learning algorithms now scan these datasets for anomalies, stars that move wrong, flicker oddly, or vanish without explanation. In 2022, an AI sifting through Gaia satellite data flagged a handful of stars exhibiting impossible accelerations, later theorized to be tugged by unseen black holes. Similar systems might one day spot the infrared glow of a population, 3-star hiding in a void, or catch the gravitational ripple of a mirror matter star warping a galaxy's rotation. But for all these tools, the hunt remains maddeningly indirect. Each method sees only a shadow of the truth, a bent beam of light here, a cluster of neutrinos there, leaving astronomers to piece together phantoms from fragments. The breakthrough might come from combining them, using AI to flag microlensing candidates, then neutrino detectors to confirm their identity, or cross-referencing gravitational wave events with unexplained infrared sources. It's detective work on a galactic scale, where every clue brings us closer to stars that defy not just sight, but the very laws we thought governed them. And that's the thrill, not just finding what's hidden, but discovering how much more there is to see when we learn to look beyond the light. Hidden stars aren't just cosmic oddities, they're the universe's way of humbling us, forcing us to confront how little we truly understand. Take dark matter, for example. For decades, astronomers have known galaxies spin faster than they should, their stars orbiting as if gripped by invisible hands. The usual suspect, dark matter, that enigmatic substance making up 85% of the universe's mass. But what if some of that missing mass isn't just diffuse particles but hidden stars, black dwarfs, quark stars, or even mirror matter twins lurking undetected? These phantoms could be the dark matter we've been chasing, their collective gravity stitching galaxies together without a single visible trace. Then there's galaxy formation itself. The first stars, those population 3 giants, were the architects of everything we see today. Their supernova forged the heavy elements in our blood and bones, their light ionized the cosmic fog, and their death seeded black holes that grew into galactic cores. But if a few of these pioneers still survive, hidden in voids or camouflaged by time, they'd be living fossils, windows into an era before galaxies even existed. Studying them could reveal why some galaxies clump into spirals while others sprawl as ellipticals, or how supermassive black holes appeared so startlingly early in cosmic history. The answers might not lie in the stars we see, but in the ones we've overlooked. Hidden stars also challenge the very definition of existence. We're visual creatures wired to trust what we can see. Yet the universe operates on a deeper logic, where gravity and quantum fields matter far more than visibility. A magnetic monopole star or a neutrino star doesn't need light to shape its surroundings. Its influence radiates through forces we're only beginning to map. This reshapes what it means to be in the cosmos. If a star's light never reaches us, but its gravity bends a galaxy's spine, is it any less real than the sun? Or consider Boltzmann's stars, statistical flukes that flicker into being for nanoseconds. They defy permanence, yet in that fleeting instant, they're as tangible as any pulsar. Reality, it seems, doesn't need an audience. The most profound lesson hidden stars teach is how much lies beyond our grasp. Despite our telescopes and supercomputers, we're still decoding the universe with rules written from the tiny fraction of it we can perceive. Every time we assume we've hit the edge of whether chasing dark matter or the first stars, the cosmos whispers, look harder, look differently. The next great discovery might not be a new star, but an old one we missed because we weren't asking the right questions. Or it might be something stranger, a celestial object that redefines star entirely. After all, the universe has no obligation to fit our textbooks. Its greatest marvels might not shine at all. They could be hiding in the dark, waiting for us to wise up. From the frozen phantom of the Oort Cloud to the holographic star painted onto the fabric of space-time, these 30 hidden wonders prove the universe revels in the unseen. Some defy physics, like the Kugelblitz fireflies born from pure light, or the magnetic monopole star built from particles that might not exist. Others are cosmic fugitives, fleeing faster than their own light can follow or locked behind walls of vacuum decay in alternate realities. A few aren't stars at all, just flawless illusions, like the primordial black hole masquerading as a dim sun, or the neutrino star whispering its existence through particles that slip through planets like ghosts. Each one challenges our assumptions that stars must shine, that matter must obey familiar rules, that visibility equals reality. But here's the truth that ties them all together: we've only scratched the surface. For every hidden star we've theorized, there could be a dozen more lurking in the data's noise, the telescope's blind spots, or the equations we haven't yet written. The universe doesn't hide its secrets out of spite. It's simply vaster, weirder, and more inventive than our tools can yet grasp. That's the real gift of these phantoms, not just their individual mysteries, but the reminder that discovery isn't about seeing farther, it's about learning to see differently. So tell us, which of these hidden stars left you awestruck? Were you captivated by the rogue binary twins spinning through the void? Or did the quantum foam star, blurring reality itself, make you question everything? Drop your favorites in the comments, and if you're hungry for more cosmic enigmas, hit subscribe, because the universe's greatest lesson is this: the more we uncover, the more we realize how much wonder still waits, unseen,